Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. So for today's podcast, I'm joined by Daan Moreels and Peter Leijnen, who are the founders of a fascinating company and one that is really close to my heart for people that know me and have listened to the show for a while. It's a business called Magnax, and it was created by them to commercialize and develop axial flux motor technology. So we're on to a proper motors episode today. Thanks, Daan, and thanks, Peter, for joining me.
Thank you, Ryan.
So we've got a double bubble episode here with both of you, and actually more than one business that we're going to talk about, hopefully, but the theme running all the way through will be axial flux. If we could start off, though, by just getting your backgrounds and kind of what brought you to where you are today. So Peter, could you just give us a bit of your personal background?
Sure. So I'm the original founder of Magnax. So I started the company on my own in 2015. I'm also the inventor of the motor concept. Before Magnax, I've been an engineering consultant and a mechanical designer for about 20 years, where I was mainly active in machine design, automation projects, and also some product design. So I'm a really technical guy. And currently within the company, I'm mainly in charge of long-term technological roadmap. I'm also responsible for the IP strategy.
And Dan, same question for you. Just tell us a bit about your background.
Yeah, sure. Really quick. So I'm an aeronautical engineer by training, then have been active in the market, in the corporate world for some time. Started a company with some others in 2013 around cloud computing. Exited that after 4 years, sold a part of my shares and invested that then in Magnax. How did it came? So basically I was looking for new projects in 2016. I was standing next to Peter at the school gate and asking him, okay, what are you working on or doing? I'm working on a new kind of electric motor in my garage. So I thought that might be interesting. Let's check it out. And I saw, okay, it's quite serious. He knew quite a bit about it. Did also a bit of my due diligence because he was already collaborating with the local university here, Ghent University, who was already doing research on this technology since 2009. And then we agreed that we could join forces. Me working more on the business and he working more on the technology. And that's how the initial collaboration started in 2016.
Wow. So a few years have passed by now, but maybe could you just tell us, Dan, what Magnax is and what it does as a business?
Yeah, so in the core, Magnax is a deep tech startup. So it means there is a lot of R&D research that has been going on and is still going on. So the core technology is a new motor topology that you know very well, which is called axial flux. The difference is that our technology or motor topology has one stator in the middle and two rotor discs, one on each side, which is not super new because axial flux already exists for 150 years, but it is quite challenging to make it work and also to prepare it for mass production. So that's what we have been working on since 2016, we have been spinning out two different companies around this technology. One is Traxel, which is focusing on further developing this technology for automotive, and the other one is called Axial Propulsion, which is further developing this technology for aerospace. And both markets need very low weight motors. Because that's typically what you have with axial flux is very low weight and very compact, more like a disc shape instead of a sausage form factor, which you have with a normal electric motor. And that's where the markets in automotive and aerospace are looking for.
And so this is the Taurus style, I think. Is that how sometimes it's referred to? Because it kind of looks like a donut, motor. So Peter, like back then particularly, because now it's easy with hindsight, because axial flux has gained a little bit more kind of fame or sort of awareness in the last few years. But back then it was pretty little known motor concept. What was it that led you to that particular type of motor?
Well, personally, to start with, I've always been interested in electric motors, funnily enough. So my father is also a very technical guy, and he once gave me a book about electric motors, which was still from his school time. And I think I was about 12 years old, and I was really fascinated by by the way electric motors worked. Of course, they were the standard induction motors, so no talk about axial flux motors back then. And I've also been interested in electrical vehicles since for whenever I remember. So when I was young, together with my father, we once electrified a go-kart. So we put a car battery in it and put a 12-volt motor in it. And I think it was a combination of the two which led me to really, closely follow what was happening actually in that technology. And then, of course, I noticed a small company called YASA, British company, which claimed to have invented or a better topology of electric motor. And I was very interested and very intrigued by the topology. It was back then, it was Tim Woolmer who basically came up with it. And I then immediately, I saw that this was in fact true. So if you want to build the most efficient and electromagnetically optimized motor, then it's a yokeless axial flux machine. So it has inherent electromagnetic advantages which you do not have with any other topology. So I really followed the company, their products quite closely. I followed their patents which they filed. And back then I already had the idea in the back of my head, like, okay, so what they're doing is interesting. They chose a certain technical path to solve certain problems in manufacturing, for instance. And then I already had the idea, okay, maybe it can be done differently, or at least I thought I would have done that slightly differently. But okay, I wasn't planning on doing anything with it. And then when I was still working as an independent consultant, one of my last projects actually required a very light electric motor, which we could not find on the market. And basically then I thought, okay, this axial flux topology might be very suitable for this project. We can talk a little more about it later if you want. And I basically decided to develop a generator based on, because a generator is the same as an electric motor, as your audience probably knows. And then I decided to apply this technology and to build this generator myself based on the axial flux technology and based on the design which I already had in my head for a few years. And that's actually how the company got started. So based on this generator, it got quite some attention. That's also the project that Daan saw when he came to visit me in my garage. So I was actually building that machine on my own. And that's how the whole company got started, how the ball got rolling.
What were the sort of things, like what are the differentiating features? Like what were the things that you decided you could do differently? You mentioned others in the market were working on those sort of Taurus machines. Where did you see the gaps?
Well, mainly the design for manufacturing. So I saw indeed a competitor with a performant machine, but in my eyes, it was very difficult to build and certainly to produce it in mass production. And because I had quite some experience in product design and product manufacturing, those two insights basically came together. So it occurred to me that there were actually easier ways to build this type of machine. So electromagnetically, almost identical. You have the Oculus axial flux topology, but the way you implement it, the way you actually put all the components together, also the way you do the whole cooling, because that's a big challenge in this type of machine. I chose to do it in a different way.
Yeah. Okay, interesting. And Dan, to go back to you on that, the first time you saw this, can you remember what you thought of it? Was it kind of like an epiphany or?
No, totally not. Not totally not epiphany. So of course I came out cloud computing, so that was completely new kind of technology for me. I've seen electric motors in my engineering university years, of course, but I had to dig in decently. I have been talking with university professors and so on to check out. Okay, what do you think about it? Is also this technology potentially rightly timed in the market? Because that's also, as you know, very important for a startup to time the technology very well. And of course, at that time we were also quite naive, so we believed, okay, we will build these machines and we will put them in cars next year or the year after, and then we're off. It's it has been a lot of challenge to make it work and also to make all these preparations. So we're now with around 50 people, almost all engineers, and we are still very diligently working on the fundamental R&D, but also on the design for manufacturing part, of course. So no, initially it was unclear for me, but I think you have to have a bit of naivete in the beginning to really start with something. Because if I would have known the huge long challenge that we had ahead, I don't know if I would restart it. To be honest.
Yeah, if only you knew then what you knew now.
Yeah, that would have made a big difference indeed. But yeah. That's history, of course, and that's how new innovations are deployed. So I'm happy to have had this experience.
Peter, on the axial flux machines, I mean, some people will know it's a concept that's been around for a long time. Some people might not have heard of it, though. So can you just tell us what we mean by axial flux?
Yeah, so the name axial is referring to the direction of the magnetic flux inside the machine. So an electric motor works by interacting electric flux from the stator to the rotor. And a lot of machines nowadays, certainly EV motors, the rotor flux is generated by permanent magnets. So that's what we call a permanent magnet machine, which is gaining in popularity. It certainly has gained in popularity since the advent of the very strong neodymium magnets. So they more or less caused a breakthrough in permanent magnet machines. So these machines are basically the most efficient and compact and power dense machines on the market. But most machines historically have been radial flux. So with radial flux machine, you have a cylindrical stator, so that's the stationary part, and within that you have also a cylindrical rotor turning inside this stator. Historically, most motors have been built like that because, they're actually quite easy to produce. Certainly, when they were invented more than 100 years ago, these machines, but with the production methods that were available back then, those were basically the only types of motors you could build, so the radial flux ones. So with the machinery of back then, you really could not build an efficient or a good axial flux motor. Although axial flux concept itself was already invented by Faraday quite a long time ago. So actually the radial flux machine kept gaining momentum, and at a certain time, all electric motors were radial flux. So it's only since very recently that the axial flux actually is gaining traction. And the reason is, I think, manufacturing capabilities. But well, two things: design capabilities and manufacturing capabilities. So to design an axial flux motor, you really need to do quite complicated 3D simulations, because there is a 3D flux inside the machine. While a radial flux machine, you can basically slice it and do a 2D simulation. Then, and in the manufacturing, like I said, you need different manufacturing techniques. You need some quite advanced polymer materials as well to be able to build a stator. It's also a bit more difficult to assemble the machine as well. You need some tighter tolerances in some places. And all those things only became available for the last, let's say, 10 or 15 years, basically.
It's interesting you mentioned, because I often heard, and in fact I said myself, that issue around three-dimensional magnetic design, and that being a really big limitation of the initial sort of, or the progress in axial flux, because it really is just like the last couple of years that those design tools have become widely available where you can do three-dimensional magnetic flux design. So the question for you, I guess, would be, how on earth were you managing to do that before those tools were available? Did you create your own design tools, or did you find a different approach? So how did you manage to overcome that design issue?
Well, actually, when we started designing the motors, and even before, like when YASA started their development, those tools were already available. They had to be modified. Like we also had to build our own models, but the calculation software itself was actually already available. It was not very user friendly, so it took a lot of effort to really get the results from it which you wanted. But it was already possible. While for the radial flux motors, that was almost automated. You just put in the parameters which you wanted from the motor, and the software basically generated the whole optimized design already. So it took a lot more manual effort and engineering work to really get to a good electromagnetic design.
And on top of the electromagnetics, the other challenge area with axial flux, and actually you mentioned it earlier, is the more complex thermal pathway, so getting the heat out of the machine. What kind of design approach did you employ to work that out?
Yeah, so indeed on the cooling, well, the machines are much more power and torque dense than a typical radial flux machine. So we are talking about 2 to 3 times the power and torque density of a high-end radial flux motor, which is of course very interesting. But if you have more or less the same efficiency between the radial flux and the axial flux motor, that means that you have to extract the same amount of waste heat from a much smaller volume, basically. So that's why you need a much more performant cooling architecture. It's much more demanding. So basically the only solution which is possible is doing direct cooling, direct liquid cooling, where you directly extract the heat with the liquid from where it's generated. So meaning directly cooling the coils, the copper, even the bus bars. In our case, we even directly cool the magnets, the rotors. So everything which generates heat gets directly cooled by, well, in our case, oil.
Is it like an oil spray or oil spray inside the motor?
For the rotor, it's more or less it's like a spray. Yes. For the stator, it's quite intricate flow pattern that's generated inside the stator.
Just even getting to that point, was it experimental research that kind of helped you get there? Or because like you said, with the radial flux motor, you have these tools that are pretty much automated for the EM, but also for the thermal, and you come out with a model, it's reasonably close, a bit of an experimentation. But for the axial, you might have had the electromagnetic design, but were you getting the sort of thermal design as well out of the tools, or were you having to,
So it was a lot of experimentation, like you said. The flow tools, they are available, but the problem there is that to get a good simulation, it's extremely difficult. So if you really want to have, basically it's you can only start doing these flow simulations or thermal flow simulations once you really already have defined your concept and already refined it. I did not find it useful to get started with these kind of simulations. So you just took a hands-on approach, built a lot of prototypes, and just saw what performed the best. So a prototype with a lot of temperature sensors in it, let it run and see how it performs. Yeah.
Tell us about the business concept of Magnax. So how's the company structured? What's the business there to do? Because that's quite an interesting feature.
On the Magnax level, actually what we understood at a certain point in the histories was that there was a big tier one called Magna active in the automotive world, and when we switched from the wind turbine business, which was quite conservative, that's why we switched to a field of smaller high-speed motors. We were active in automotive, and there we had Magna. So in exhibitions, they started to ask us, are you like the experimental division of Magna or something? And then we understood, okay, maybe we have to switch to a different name. And then we also understood we received quite some incoming sales leads from the aerospace world also. So we saw, okay, this technology might be useful for different kind of markets. And then we thought, okay, maybe we should just structure Magnax as a holding company, which is taking in the investments. So yeah, we gathered around 36 million euros of investment money, and then organized the company as such that the daughter companies are operationally organized, focusing on their respective markets. Then you could ask, okay, why separate teams? But we noticed that if you try to engineer both automotive and aerospace products together with the same engineering team, that's not working very well, because the specifications, the market timing is quite different in these markets. And also, in aerospace, it's all weight reduction that counts, but in automotive, it's all about cost reduction, making sure that you can build hundreds of thousands of these motors, where cost is very important, where aerospace, it's all about weight reduction. So that's a completely different engineering philosophy. Therefore, we organized separate companies and separate engineering teams. Another reason is also, this is deep technology, it is strategic technology. So in terms of exit scenario, it's also important to try to debundle things up front, because if for some reason the axial company wants to work with Airbus says, okay, sorry, but I don't want to see that your automotive division is completely attached to this. I don't want them to check our things out. So there has to be a wall in between, and there is no better wall, of course, if you have separate companies.
Yeah, and is the model going to be, or is the model like sort of technology development and then partnering, sort of licensing, or do you plan to get into production? Are you setting up a plant, or what's the actual sort of business model going to be?
Yeah, and the business model is indeed, we are a technology company, so we don't have the ambition to deploy manufacturing facilities. For the main reason I'm talking about our automotive part now is because the bigger OEMs with who we are working, they do have their own resources. They have a lot of people. They are already specialized in gearboxes and sometimes powertrains. So we see more and more a trend of completely insourcing the technology directly into the OEM. They are very good at deploying facilities, and they have people. So we focus on what we are good at, which is developing the technology, making sure that we have the A and B samples, that the prototypes are also prepared for mass production. And then the customers, together with them, we further develop it into powertrains, and they are really good at the manufacturing part anyway.
And is that typical customer on the automotive side a tier one, or is it an automotive OEM? I'm interested because there's a lot of discussion at the moment about verticalization on the OEM side, which has sort of come back around. The OEMs got rid of all of their internal tier suppliers years and years ago, but because of the fight with Tesla and their kind of approach, people seem to be opening it, but are you effectively enabling that, or are you still with the tier ones as well?
We don't make a choice, but what we see is indeed the trend that OEMs are more and more insourcing technologies directly. And that's a strategic thing, of course. You see that also, it has also its advantages. If you see that Tesla is developing everything in-house, they can completely attach the complete supply chain in one philosophy, in one strategic portfolio. It seems smart to us also to attach our business model to that one, but we don't say no to tier ones if they have the vision and it complies with ours. Why not? Of course.
And I probably know the answer to this before I even ask it, but you're able to give us any names? Tell us who you're working with.
Yeah, you know the answer, but indeed we have very strict NDAs, and as you know, these companies, they don't want competitors know that they are potentially working with this new technology. So that's why we have to have these NDAs. So this is, as I said, strategic technology. That's a bit a pity from a marketing point of view, of course.
Build those case studies. It's fair to say, though, that you are working with some very big OEs and tier ones.
Exactly.
Swinging back around, so Peter, the normal debate on axial technology tends to come down to, with radial flux motor, that the direction people have gone for high power density is these high speed machines. So sort of 20,000 RPM plus, I think 22,000 is a bit of a magic number at the moment. Obviously, axial flux doesn't tend to be high speed machines. It's a different approach. But what would you say? What's your position in terms of the competitiveness of the axial technology compared to high speed radial?
So it's true that, of course, to generate power, you have to multiply the motor's torque by the speed, and the easiest way to gain power is just to increase the speed of the motor. That's basically power which you get for free. So that's why, of course, most motor manufacturers try to increase the speed as much as possible, where the typical limit is actually the centrifugal force on the rotor. So that's the limit. If you would go higher in speed, the rotor would basically explode. So that's all good and well. But of course, if you do that, if you just keep increasing the power by increasing the speed, you also create a few problems down the line. For instance, NVH becomes a real challenge. But also, this high speed, of course, has to be brought down to the wheel speed of the vehicle. So you need to go to transmission. And of course, the higher you go in motor speed, the larger the transmission ratio becomes. And a big transmission ratio, you would typically, the higher you go, the more gears or the more gear sets that you also need. So the biggest problem that I see is basically the efficiency of the gearbox. So you really do everything to push the efficiency of the motor up to the last 0.5% point. But then you lose efficiency because your speed has to be brought down so much. So if you have to add one gear stage, you easily lose 1% efficiency over your entire efficiency map, which is basically huge. So that's why we basically take another approach by trying to generate as much torque as possible from a certain motor size, certain motor volume, and not go so high in speed. So for an axial flux machine, the top nominal speed is typically between, let's say, 10 to 12,000 RPM, something like that. Maybe a bit higher as well in the future, but the torque is much higher compared to a radial flux motor. So even though the motors then have the same efficiency over their entire efficiency map, you would still get a higher driving efficiency because your gearbox the gear ratio is much lower, much smaller. So that's where you have an efficiency benefit. And of course, then you also have the weight of the gearbox. A smaller gearbox is much less weight as well. So both the motor and the gearbox are much lower in weight. And that's where the compounding effect starts, because then because you have this higher efficiency, you also need a little less battery. and then the vehicle is even lighter, and then it's even more efficient, and it starts compounding.
So it's one of these sort of system level. If you look at the components in isolation, maybe the difference is not so interesting, but at a system level, it becomes much more. You mentioned about the speed of an axial machine there, and that's something. It's an interesting thing. I think people will be interested in. What is it that limits the speed of an axial machine?
Well, that's easy. It's the size of the rotor, because the motor topology looks more like a disc rather than a cylinder. The diameter tends to be bigger than for a radial flux motor. So let's say for an automotive axial flux machine, the rotor diameter would be something like, let's say, 240 or 250 millimeters. While for the same power, a radial flux motor would be more like 120, 130 millimeters. So that's a huge difference in size. And of course, the centrifugal force is basically a square function of diameter of the rotor. So that means that the centrifugal force gets much higher really quickly at the farther you, or the bigger you make your rotors. So that's what limits the speed of the rotor, well, both in radial and in axial flux machines.
So it's kind of the thing that gives it its strength. It's the surface area and the size of the rotor is the thing that gives it the limit as well. You mentioned 12K being the sort of nominal max for now. What is it that could extend that speed range?
We are working on that. So we see possible routes towards higher speeds. I don't expect we will reach 20,000 RPM with this size of motor, so typical automotive. But I think that somewhere close to 14 or 15,000 RPM should be possible, and that's just by improving the mechanical design of the rotor. So incorporating some high strength materials as well. But it's a very complicated thing because you are working with different materials. So the rotor has different functions. It's an electromagnetic function. It also has a mechanical function. You also have to deal with NVH, with vibrations, magnetic forces, quite vulnerable magnets as well. So they are mechanically quite vulnerable, but also thermally. So there is typically a very strict temperature limit on the magnets. So the higher you go in speed, the higher your losses also become in the magnet. So the hotter they get as well. So you really need a very good cooling system as well to extract the heat from these magnets. And that all becomes much more important the higher you go in speed. So there is probably a practical limit where you would not really want to go above, because it would create so much other issues that it's not worth the trouble anymore. And I guess it's around 14 or 15,000 RPM nominal speed.
And that would fit in quite nicely with not having to get into exotic gearbox technology and
So our goal is to work with basically a planetary gearbox. So the motor topology, also the size, really lends itself well to a combination with a planetary gearbox, and preferably a single stage planetary gearbox, because that's also a very light gearbox topology. It needs a certain diameter, which fits our motor as well, and they seem to be made for each other. So
nevertheless, we also see advantages in combination with lay shaft gearboxes, because we saw a case where, in combination with the high-speed radial flux motor, to get to the power, they really had to use a dual-speed gearbox, but they got the necessary torque at a much lower speed with axial flux motors, so they could basically reduce the complexity of the gearbox significantly, which also led to a certain capex reduction on the gearbox level.
So going from a 2-speed transmission to a single speed was enabled
by using an axial flux motor, because you get the required torque at a lower speed, basically.
Well, one question I've got noted down, and Peter, you mentioned this. You mentioned NVH particularly with the Taurus style machine, one of the things that's often discussed is the torque ripple from that machine compared to some other motor topologies. What is it? What have you guys done in terms of addressing torque ripple and noise from the machine that is making it better in the market?
So I think torque ripple, if we are on the same level as the typical radial flux machine already, I think we are, well, the main reason is that we use concentrated windings. So fractional slot concentrated windings, they tend to lower the torque ripple of a permanent magnet machine, where the most radial flux machines, they are distributed winding, and they tend to suffer more. It's counterintuitive, in fact, but they suffer more from torque ripple. So that's one thing. Then the second is to have the right pole slot combination in the machine. As you know, you can have different numbers of magnets and different numbers then of stator teeth or coils, and they all create different properties or different advantages, different disadvantages. So by choosing the right one, you can also minimize torque ripple as well. There are, of course, some other things you can do to further minimize it, like shaping the magnets, giving them a certain shape. And then you are already at a really acceptable torque ripple level. What you can further do, and that's quite a modern technique, is implementing a certain control strategy in your inverter, which further reduces the torque ripple. So that's something we are also working on at the moment, which also seems quite powerful. So I think that issue is actually completely under control.
And you mentioned inverters there. Is that a technology area that you guys have been working in, or do you tend to work with a partner for inverter technology?
No, we are developing our own inverter, so silicon carbide inverter. We actually decided to start that project quite some time ago, because we realized that the motor and the inverter, they are like brother and sister. They really have to be developed together to be able to work in the most optimum.
To get along nicely.
To get along nicely. Yeah, indeed. So you can, of course, buy an inverter, but we do that. And we have also some standard inverters for on the test bench, etc. The motors work nicely with it, but to push the combination, the ultimate, you basically need to design them together.
Yeah, it's a bit like what the Lucid CEO said like 2 years ago. If you expect a really state-of-the-art powertrain design, you cannot expect that if you're combining different off-the-shelf components. You have to look at it from a holistic way. And as you can see, their powertrain is also pretty good. It's a radial flux one, but it's a nice one.
I always think, I remember talking about this years ago, like a high degree of integration. You know, if you've got lots of disparate component sets, and in a funny way, as electrification's emerged in industry, that's, I think in automotive in particular, that's been one of the big changes in mindset. Is everything's integrated now. So in the past, you'd have a team that worked on engine cooling and a different team that worked on cabin HVAC, and it's the same thing now, and they have to get along nicely. And the sort of electronics was separate to the powertrain, whereas now it's inescapably part of it. And that high degree of integration is very critical, which makes it hard as unless you're a fully integrated tier supplier, which a lot of them are. But it does make it difficult. You selling a standalone inverter or standalone motor these days for volume automotive would be a pretty difficult proposition, I think. And coming back to you, Dan, what is it? What does the future look like for Magnax? What do you see coming up in the next year or two from a business perspective that's got you excited?
Well, I think in the future we will be still busy for a long time because, as Peter said, axial flux technology is pretty young technology. So we're currently working on the second generation of this technology, but we see radial flux is already in its 6th generation. So it has been also going through a lot of incremental improvements over the last 30 years. So we see the same happening with axial flux, which means that although the technology is already performing pretty well, it still has a lot of room for further improvements going to generation 3 and 4. So our goal is to start with generation 2 in terms of collaborations with OEMs, and then also they can use our next generations also as further improvements for their powertrains if they choose for axial flux, of course. So our future is keep doing, keep innovating, and making sure that we can also evolve this technology to something which is a really robust alternative in some cases for radial flux motors.
And what do you think of the aero market? And I'm particularly thinking eVTOLs, because in some ways, I mean, one application that is great for axial machines is for fan drives, and obviously an eVTOL is kind of a number of big fans. Do you see eVTOL kind of applications developing for axial flux?
Yes, this market is of course a lot less mature. I think eVTOL is 10-15 years behind automotive, maybe a bit more. The certification aspect is quite difficult, and what we see is, especially in an eVTOL, they are combining multiple technologies like new motor technology, but also like hydrogen fuel cell technology and very strange ways to propel these vehicles. So that takes some time. So the certification aspect is something that we have to take into account. But focusing on our technology, it is by design an effective technology in terms of power density. And for aerospace, weight reduction is everything. And if you have like 6 propulsion systems, on average 6-7 per eVTOL, and you can reduce 10-20 kgs per motor, per propulsion system, then you can basically add one additional person in the vehicle. So that does make sense. That's why axial flux, especially from the academic world, is taken into consideration immediately for aerospace applications.
And in aero, like maybe more, it's a funny thing to say about aerospace because everything takes so long. In aerospace, obviously the eVTOL is a future tech, but there's a lot happening today around the electrification of aircraft generally, and kind of hybrid systems and electric actuation and things. And that, again, that's something axial technology could lend itself to really well. Do you see demand coming through for that kind of thing, for electric drives for sort of more electrified aircraft rather than full out electric aircraft?
Larger aircraft. Well, we already see it and for pilot trainers, for instance. But okay, these are full electric little aircrafts where you want to train pilots 10, 15, 20 minutes is enough. For larger aircraft, it will electrify, but I see it more as a hybrid application where you're going to use still sustainable aerofuels, for instance, but combine that with electrification to also reduce CO2 level and also noise. If you can take off electrically on an electrical way, then the noise will be lower. You can still operate in certain circumstances at night, for instance, or you can just optimize for the moments that your normal engine, your conventional engine, is warmer, or use it in the right circumstances. So that will further reduce indeed CO2 levels. But fully electrified aircraft, especially for larger aircraft, 94 people or more, I'm not sure. Maybe in 80 years or something, but not with a battery.
Yeah, a long time. Cool. And Peter, just sort of looking forwards, like same question, but from a technology point of view, with your business, with your technology, I mean, it could be in the industry. What's the thing that's getting you excited?
Basically what we are doing at the moment. So I think I don't expect some really big technological jumps in the technology. I think you will see a gradual improvement of the technology itself, because we still see quite some possibilities to keep improving it. But for us, we are mainly looking out to the adoption of the technology by the OEMs. So like you said, they are quite conservative, they have a lot of other problems on their minds at the moment. Some of them are, of course, looking further, looking a few years ahead on the technology front, and are really interested in axial flux technology. But a lot of others are still over their heads in the reorganization and in trying to figure out what they have to do with their workforce, trying to figure out how they can actually make a profit out of EVs, trying to figure out what they're going to do with their battery materials, how they're going to source it, make it less dependent on certain single suppliers, for instance. So then it's difficult to get their attention, even if you have fantastic technology. So, but I think this time, this point will in the quite near future, they will be much more open to it when the dust has a little bit settled down a little bit. And they find they really know what they basically want to do and have a real EV strategy, and we have to be ready by then, of course, to completely demonstrate the technology, that it's validated, that it can be produced, that is basically ready to go. Of course, I also expect Mercedes-Benz by then to have been showing off the technology in their AMG cars, which I expect to be quite impressive, actually, if they use the technology in the right way, which I'm sure they will, and that will, of course, give another boost to the interest in the technology.
Be an exciting time for you to see, what started in your garage get into production and vehicles running around on the road, using that technology. Immensely satisfying for both of you. It's been a tremendous journey that you've been on. So, I mean, that's fantastic. That's, I think, all we have time for today. Leaves me to finish off by saying, so people will see down in the show notes, we'll put some links in so you can find these guys and find Magnax and follow up with them if you're interested. Thank you so much for joining me today, Daan and Peter. It's been really nice to get this opportunity to talk in some more depth, and hopefully I'll see you in the real world soon.
Likewise,
Ryan. It was very nice to talk to you.